particular lecture we will be basically discussing about the those, we'll actually extend those topics, okay. So we'll discussing in terms of the algorithms, okay. So for every relational operators, actually the way it appears in the query, we will have a particular algorithmic view of applying the different access paths, okay. So first operation is the selection operation, right? So in the selection operations, say with respect to the file organization used in the relation, that is various situations with respect to the file organizations used in the relation. So availability of indexes we'll discuss on the algorithm that we'll be applying on it, okay. So if we have a simple query like this, where you are trying to retrieve the tuples, that is the select star from a particular table reserve R, for particular relation reserve R, where the R name is equal to 0. So the condition here, the relational condition here is the equality condition, okay. So that actually looks for those tuples where the R name field is 0, okay. So that matches the 0. So on the tables that we are considering, the background relation that we are considering are suppose the sailors and the reserves, okay. Now there can be many possibilities given those selection operations, okay. So one possibility is that for the attribute which you are looking for in that particular selection condition, okay, selection operation, that may not have any index available for it in the relation, or the background relation may not also be sorted on that particular order, on that particular attribute, okay. We do not have a sorted order for that particular attribute so based on the attribute that is specified in the selection condition, so you have to first look for whether there is an index available in the background relation or the background relation is sorted on that particular attribute, okay. If we do not have any of this, obviously the file scanning is the only option left for us to identify the tuples, okay. That is for linearly scanning the file from one end to the another end of that particular relation, okay. So that becomes the only option available for us to retrieve the tuples from that relation, okay. Now that is one option where you don't have any index or a sorted order for the attribute. Next is, suppose if you do not have an index on that particular attribute, but the background relation is sorted on that particular attribute, okay. If we have such kind of situation where we have a sorted order for that particular attribute, you see here, this is the selection condition, right? R attribute operation here, value R. That means this is the value for the relation domain and which matches with the particular operation specified in the that is the selection operation, okay. So if we have a sorted order for that particular attribute, ATTR and the relation, that is for the attribute, then we can take advantage of the sorted order to identify the first tuple through binary search, okay, because we know that for precondition of binary search is the sorted order, okay. So we can actually do a binary search on the relation to identify the first tuple of the matching criteria, okay. So once the first tuple of the matching criteria is identified, so then we can actually go on retrieving the other tuples from there on, okay. So that we can actually go on scanning the R from there on, from the first tuple there that is identified through the binary search, and that until the selection condition no longer satisfied, we can actually go on retrieving the tuples, okay. So that is how we can take advantage of the sorted order on the attributes. Similarly, if we have a B plus tree index, so if the particular attribute is part of an index file, that is we have a B plus tree index on that particular attribute, okay, the attribute which we are using in the selection condition, okay. So if we have a B plus tree in the attribute, that is the index, then we can actually identify that particular those qualifying, that is we can identify the first tuple, okay, that is to find the first index entry that points to the qualifying tuple of R, okay. So we can go on actually to identify the first index that points to the qualifying tuple of R, and then we can scan the leaf pages of that B plus tree index to identify the rest of the tuples, okay, unless the selection criteria is satisfied, okay. So what we can do here is that we can take advantage of that particular B plus tree index of that particular attribute, okay, index file on that particular attribute, to identify the first index, okay, that is through the tree, that is the B plus tree, to identify the first index in the leaf node, okay. And then we can actually, till the criteria is satisfied, we can go on retrieving the tuples from the, by following the leaf nodes in the B plus tree, okay. The cost of retrieving using the B plus tree is actually depends on how many tuples you are retrieving using the B plus tree, okay, and whether that particular tree index is clustered, okay. That is, if we have an attribute, suppose this way, the selection attribute, R attribute with the operation some value, some constant, and the attribute have a B plus tree index, then for the retrieving, if it has a clustered index, then it may be only one IO operation. That is, the cost may be only to retrieve one page because it is clustered, okay. So it is, so that is just, it may lead to only one IO operation, or the cost only one page retrieval from the backend, okay. So, and of course the cost of traversal from the root to that particular leaf node included there, and one IO operation is enough for this one if the clustered index is available. If the B plus tree index is not clustered, okay, so in that case, it of course the cost of using the index depends on the number of tuples that actually satisfy the selection. So if we are not fortunate enough that the attribute specified in the query is in the clustered index, if there is a B plus tree index but it is unclustered, that is the criteria 2 and 3, okay. If that happens, then obviously the cost of retrieval, the number of page retrieval, IO operations, depends on the number of tuples that you are going to retrieve, okay. Suppose if you have some 10,000 tuples to be retrieved given a particular criteria, selection condition in the query, okay, and suppose those 10,000 tuples are distributed in some 100 pages, okay. So clustered index actually can actually be, if there is a clustered index available for that attribute, then obviously we can actually retrieve the 100 pages that actually those, see the selection condition that is being specified in the query actually can retrieve the tuples which can be accommodated in some 100 pages, okay. So if we have a clustered index available for that particular attribute, then only 100 IO operation is enough to retrieve the tuples from those, you know, from the list, from the size of the tuples in the relation, which is actually 10,000, okay. Suppose there are 10,000 tuples are there, okay. So we can actually just get those tuples by using 100 IO operation if it is clustered, okay. Now if it is unclustered and we are not that fortunate, then we may require actually 10,000 different IO operations, because each tuple may refer to some different pages in the backend, okay. It may be stored in the memory in different pages, and so we may require 10,000 different IO operations, because for every tuple we may have to retrieve their different pages, okay. In that case we will be requiring 10,000 different IOs if we are not fortunate to have it through the clustered indexing, okay. So that is how it depends on how many tuples are retrieved by a particular criteria, in the selection operation. Okay. So depending on that, if unclustered, the IO, the cost of retrieval will be determined. Now, if instead of the B plus tree index, if we have a hash index. So hash index basically has a very typical advantage, that is, if there is equality condition, selection operation is equality. Okay, in that case, hash index performs better than the B plus tree index. Okay, so it is, if we have a operation specified this way and that is equality condition, then obviously we will go for hash index if the hash index is available. Okay, so general selection condition. Till now, the selection condition that we have we are discussing is basically on one single selection condition. Okay. Now, the general selection conditions may be the combination of some and or between the different terms. Okay, where the selection conditions are being applied. Now, so as you know, in the linear algebra term, we actually specify and by this value, right? So here, attribute of a relation. So if attribute value of a relation may be operation with a constant value, it can be combined. Okay, or it may be combined with the attribute 1 of one relation with the attribute 1 of attribute 2 of another relation. Okay, so we may have something, you know, may have something referred to, that is, suppose say the relation R dot R name is equal to, suppose, some value. Okay, and suppose the BID, the board ID, is R. Okay, so when we convert this particular general condition to a relational algebra expression, what we have the selection condition, that is R dot R name is equal to Joe, and specified this way, and that is the R dot. Okay, that is how we specify, and of course this is for R here. Okay, now given this relational algebra expression, we have different options to evaluate it. Okay, normally, as we discussed in the earlier chapter, that is, we go for conjunctive normal form. So the relations, that relational algebra expression, this and operations, we convert it to the conjunctive normal form and then apply the different access path on it. Okay, so conjunctive normal form, if we have a CNF and some matching indexes, then what to do? Okay, so if we have a conjunctive normal form and the indexes on the attributes, then we can follow certain access path. So that is, suppose that we have a selection on the reserve with the condition this day is less than some day, okay, that date value, and then the relational name is given by, R name is given by Joe, okay, or BID, okay, is equal to 5. So when we have a condition specified this way, we can convert it to conjunctive normal form, that is, say day is less than, for some of the day, okay, some value, is given by the okay. We have a junction here with the BID is equal to BID is equal to 5. This junction is suppose SID equal to 3. Now, in this case, we can convert it to a conjunctive normal form by through this way, that is the day less than 8, 5. Okay, so given this, and here, and then we have the R name to okay, or we have a conjunctive normal form, and now we can have the access path defined on these indexes by using the defined algorithms for accessing the selection path. So we have a uniformity here, so we can use the access path by using the conjunctive normal form. Now, evaluating the selection conditions without disjunction. Suppose if we do not have a disjunction in that particular general selection condition, then how to evaluate it, the selection conditions. Okay, so what we can do, we can have, suppose we have a single index available on a particular attribute, okay, on a prime attribute. We can retrieve that using that particular for that particular conjunct, the term. We can retrieve the tuples by using that particular index on that, and then we can apply the non-prime conjunct, the other on which the attribute the index is not available. We can apply that particular conjunct on that retrieved tuple which we have retrieved using the index, and we can get the we can actually apply it on it, and we can get a reduced set of tuples. Okay, so what we can do, basically, if we have only conjuncts in the selection condition, then and we have attribute on a particular part of that we have index on some particular set of attributes on that particular conjunctive normal form. Okay, so we can apply that particular index with those attributes which are on which we have the index available, and we can get the tuples from the relations by using the index, and then we can apply the non-prime index where we don't have any index available on those retrieved tuples, and we can have the reduced set. Okay, that is what is that is how we can have a reduced set by applying that is the indexes on the conditions where we don't have a disjunct. We do not have a disjunct here. Okay, only conjuncts are there in the conjunctive normal form. Okay, so if we have more than one index available, then we can obviously go for applying all of those indexes, and we can go for the intersection. Suppose if we have in the attribute if we have the attribute and those we have index available on day and BID, okay, but multiple indexes are available, but those are not clustered, unclustered indexes. For clustering it is simple, because in case of clustering, clustered index available, first you go for the clustered index access path, okay, because that will give you the minimal number of pages to be retrieved. Okay, so retrieve those tuples and then apply the non-prime, that is the non-index conjuncts on that to get the reduced set. So if you have the indexes but they are not clustered indexes. So what you can do, you can basically retrieve the tuple by using the, first you retrieve the set of the record IDs, okay, which are available. Only the RIDs, you know that with the clause 2 and clause 3 means they actually take RID for the unclustered indexes. Okay, so set of RIDs for the day, set of RIDs for the BID. Okay, if you have suppose 2 unclustered indexes available on these 2, okay, then what you do after retrieving these RIDs, you take the intersection of these 2 sets. Suppose if you are from the day, if you get the RID set 1 and for this you get RID set 2, then just take the intersection of these 2 to say get the common RIDs from these 2 and then retrieve the tuples using that common RID set. Okay, and then apply other conjunct which is the SID for index on the retrieved tuples to get the reduced set. Okay, that is how you, when you have the multiple indexes, several indexes available to be used while deriving the tuples from the general selection conditions where you have only conjuncts. Conjunctive normal form have only conjuncts, not disjuncts. Okay. Now, if you have the selection conditions with disjuncts, okay, if you have some disjuncts in the selection conditions, then how it is to be used? So there are different evaluation options can be considered depending on the availability of indexes on the and sort orders. Okay. So given if you have the general selection condition on disjuncts, the selections which have disjuncts in between, so there can be several evaluation options which can be considered depending on the availability of the indexes. Okay. So every term in a disjunct has a matching index. So if every term on the disjunct have a matching index, then what you can do, suppose you have this, you know, so every term in the disjunct suppose have a matching index, then what you can do, you can apply those, you know, those indexes to retrieve the tuples, and then you can take the union of those two, those retrieved tuples. So suppose you have it. So apply B plus 3 index. So B plus 3 index on this day to retrieve the tuples which matches this criteria. Okay. That part to retrieve the tuples which matches this criteria. Okay. And after those tuples are being retrieved, you just take the union. You take the union of the retrieved tuples. Okay, you need to take the union of the retrieved tuples to get the final result. Okay, that is what needs to be done when you have the disjuncts. Okay. So if all the matching indexes have the unclustered indexing, that is the alternative 2 and 3 for the data entries, then what you have to do? Suppose you have these criteria here again. Available, but the index availables are unclustered. Okay. So what you have to do, you have to take the set of RIDs from both criteria. So you get the RID set, RID from here. Sort those RIDs and then take the union. Okay, take the union of this set of RIDs. Okay. So you have to basically take the union of this set of RIDs and then sort them by the page number and retrieve the actual tuples from the reserve. Okay. So we can take we can find the RIDs for this particular, for this criteria. We can find for this criteria. Okay. For this using the index on the RName and index of the set of RIDs and sort them by the page numbers. And then you sort both by the page numbers and finally you retrieve the tuples from the reserve based on the sorted order. Okay. So what you have to do, you have to basically take the union of the RIDs first. Okay. So if there is no suitable indexes or the sort order for those fields, then obviously if you have the disjunct of them, then you have to go for the file scan. Okay. If you do not have any index or the sort order available for any of these terms which are specified in the disjunction, that is the general the expression, the relational expression that is being derived, which has disjuncts in them, then what you have to do, you have no alternative but to go for the file scan. Okay. So that is how this should be. Now for the projection operation, to implement projection, we have to do the following. What we have to do first, as you know, what is projection? Projection is actually, it is indicated by this symbol, right? In the projection, in the relational algebra expressions, right? We indicate the projection by this. This is the symbol for projection. Now, for projection, those attributes which are specified in the select clauses, that is, remove the unwanted attributes which are not specified in the projection expression. So that is what we need to do first. And then once we remove the attributes from the relation, directly the attributes from the relation, we may, if the primary, the keys are not there in that particular set of attributes, then we are going to get some duplicates. Okay. So the next set of operations, if we have to retrieve the distinct values, we need to eliminate the duplicates. Okay. First, we need to select the attributes which are specified in the select clause, and then obviously it is the in the projection, the query, you have that particular attributes which are specified. Then we have to go for the removal of the unwanted attributes in the relation from there, because we want only a specific set of attributes. And once we have those tuples corresponding to those attributes, we have to identify the duplicates and remove the duplicates. Okay. We have a query. Select some obviously for that is given by, for the relational algebra expression from this particular query, will be nothing but SID, comma, GID, reserve. Okay. So when we convert it to the relational algebra expression, we get this. Okay. Because we are retrieving these tuples from the reserves, right? So in general, we call it the list of attributes with that particular symbol, the projection symbol. Okay. So projections can be done on the projection based on sorting or projection based on hashing. Okay. So let us first discuss about how to do the projection on sorting. So algorithm based on sorting has the following steps. Okay, that is, first you scan the R, the relation, to produce a set of tuples that contain only the desired attributes. Okay, so you need a set of attributes. See, you are not selecting row wise. Actually, you are selecting the column wise, right? Because the attributes are attributes are specified in the column. So when you are selecting the tuples, you are selecting some values which corresponds to the specified list of attributes which you want to project, right? So first you scan the R to get those set of tuples which contains only those attributes values in the column list, right? So after this, what you need to do, you need to sort these tuples that you have retrieved using the combination of all the attributes as the key for sorting. Okay, so as the combination of all the attributes as the key for sorting, you have to sort this particular set of tuples that you have retrieved. Okay, now once you sort, what will happen? Those which have the duplicate values will be in consecutive list. Okay, so they are in the adjacent, they will be adjacent tuples, right? So what you need to do, you need to remove the duplicates. You need to delete the duplicates from there to get the distinct tuples. Okay. Projection based on hashing. So we know that when we use a hash function on some attribute list on the tuples, we get those tuples in terms of buckets, right? So in the hash-based approach is advantageous because when we apply the hash functions, we get certain different, you can say, combination of tuples in different buckets. Okay, so there can be there can be a partition phase. Now when we apply the hashing for the projection, we have actually two phases. One is called as the partitioning phase, another is called as the duplicate elimination phase. Okay, in the partitioning phase, we have one input buffer phase. First I must tell you that this particular projection based on hashing is most suitable when we have a large amount of buffer space, say as indicated by B number of pages for buffer, okay, based on some the number of pages from the relation that has to be retrieved. Okay, suppose if we have a large number of pages to be used as buffer, then obviously hashing approach, instead of sorting, the hashing becomes an advantageous approach. Okay, so suppose there are B number of pages, fairly large B number of pages for the buffer. Okay, for the pages related to the number of pages R. Okay, so we can use the hash-based approach for the this is what using the hash-based approach for the projection. Now here in the projection phase, what we will do in this phase, we have one input buffer phase which is taken as the for taking the inputs from the backend, because we will be retrieving the tuples page by page from the backend. Okay, so there will be one buffer phase which will be taken as the input buffer phase from those list of B pages, and B-1 buffer phase as the output buffer phase. Okay, for outputting buffer pages means when we have applied the hash functions, whatever different segments of tuples being created for different values of the hash functions, those will be in different output buffer pages. Okay, so there will be B-1 output buffer pages will be used for that. Okay, so following is the set of the steps to be performed. So what you will do, you will basically retrieve the relation R into the input buffer page one page at a time. So from the backend, the one page at a time you will take as the input to the input buffer page. Okay, so after that, for each tuple that you retrieve from the backend, you just remove the unwanted attributes. Okay, because those attributes which are not listed in the projection query, in the projection list of attributes, you remove those attributes. Okay, and then apply the hash function H to the combination of all the remaining list of attributes. Okay, so it is the list of attributes which are required. To that those list of attributes, we apply the hash function. Okay, so after that, actually the h function, the hash function is selected in such a way that actually it gives a uniform list of the output values. Okay, so when we have distributed uniformly among the output pages, so when we have the hash function applied to those necessary attribute lists which are taken from the that is the step number 1, then we apply the hash function, and depending on the hash function, we send that particular tuple to different output buffer pages. Okay, depending on the, suppose for a particular hash value, we are sending that particular tuple to the buffer page B2. Okay, for another hash value, another tuple will be sent to the buffer page B3. That way, it will be distributed among those B-1 buffer pages or buffer pages. Okay, so it is the one input buffer page will be used to take the inputs from the backend. The pages will be read one page at a time, and it will be stored in the input buffer page. From the input buffer page, the algorithm will consider one record at a time and eliminate the unwanted attribute from there and take only the necessary attributes on which the hash function will be applied. Depending on the hash value, that particular tuple will be sent to one of the buffer pages, and that will be determined by the value of the hash function. That is the output of, that is whatever hash value that you get by using the hash function. Okay, so it is basically the partitioning phase can be illustrated with this. Okay, so there are pages in the backend which is storing the tuples of that particular relation on which the projection is to be done. Okay, so it has all the pages there, and you have B number of pages. One page you are using for input, another B-1 pages you are using for output, and you are applying the hash function here. So one page you will be retrieving here to the input buffer page. Okay, and for each tuple, what you will do, you will first eliminate the unwanted attributes. Only the necessary attributes which are listed in the query will be taken into consideration, and then hash function will be applied to those necessary attributes. Okay, so depending on the value or hash value that is generated by applying the hash function on a particular tuple, that tuple will be determined to which particular output buffer page it will go. Okay, depending on the hash value, it will be directed to one of the B-1 tables, the B-1 buffer pages, output buffer pages. Okay, so that is shown here. Okay, so after that, in the step number 2 of the partitioning phase, it will be written to one of the partitions here. There are B-1 partitions in the disk. Okay, so from the output buffer page, this one will be written to the partition phase, 2 will be written, suppose this way, it will be written to the output buffer pages. Okay, and this will be slashed out here. The fresh list will be prepared by, again the entire procedure will be repeated. Again another page will be inputted here, will be taken as the input here. Apply the hash function one by one to each of the tuples in that particular page. Okay, to the projected list of attributes. Okay, not to the unnecessary attributes. So apply the hash function, determine the different tuples which goes to the different output buffer list, and then you write it in the step number 2. You just write it to the different partitions in the disk space. Okay, depending on the output buffer page. So that is the partitioning phase, and then comes the duplicate elimination phase. In the duplicate elimination phase, there is another hash function which is being applied. Okay, so it is basically, see, first before saying this, actually we have to understand how the duplicate elimination does in the hash-based functions. Now you see, when the different partitions are being created, now each of the partitions has the tuples which have the same hash value. Okay, so there cannot be duplicate tuples in the two different partitions. Okay, So if there are some duplicate values, it has to be in the same partition. So it is we can just identify the tuples by considering one partition at a time and then just removing the duplicates from there. So how is it done? In the hash-based approach, there is another hash function, suppose h2, which is not equal to the earlier hash function. Okay, it is not equal to h. There is another hash function h2, which is applied to each of the tuple in one partition at a time. Okay, from each of the partitions, you take one tuple at a time and apply another hash function. Okay, to the and insert it into a memory hash table. You insert into a memory hash table. Okay, so again you apply h2 in another tuple. Okay, and suppose the new tuple hashes to the same value in the same existing tuple, then you can easily compare those two tuples and check whether the new tuple is a duplicate. Okay, so one tuple at a time you take from the partition, one partition you consider at a time and take one tuple from there. Apply the next hash function h2, okay, which is not equal to the earlier hash function. Then depending on that particular hash value, you send it to a memory hash table. Then take another tuple, apply h2, and if it gets the same hash value with the earlier one in the memory hash table, earlier value which you have inserted in the memory hash table, then you don't consider the new one. If you find that is a duplicate value, then you just eliminate it. You just discard the duplicate as they are detected without writing to the memory hash table. Okay, that is how the duplicate elimination can be done. So without writing the new tuple, if it gives the same hash value and you find it to be the duplicate of the earlier one, then you don't write it to the memory hash table. So once it is being, after the entire partition has been read in, what you can do, you can write the tuples in the hash table, now which is actually the memory hash table which you have created, to the result file. To the result file you can write that memory hash table and you can flash out you can clear the memory hash table and make it ready for reading the next partition. Okay, because you are considering one partition at a time, so you can use the memory hash table again to repeat the same process by using the next partition. Okay, that way you can go on doing till all the partitions are being covered and it will give you the duplicate element. Thank you. In the particular, the table that we have actually in this class we have discussed we have used the algorithmic approach for evaluation of the selection operations as well as the position operations, where through which we can have the best possible access path, okay, most selective access path for execution, right? So we have we have actually discussed here in this class. So we can say these are the algorithmic approach for applying the access paths to those operations, right? So thank you, and in the next class we'll be discussing the join operations.